Taking a look at the last example of graphing sine functions, we are going to work with this example now where y is equal to a sine bx minus c. So we have a and b, amplitude, and this changes up or maybe not our period. And we know from the graphs we've already done using this A and B information that they represent shape changes to our sine function, either a horizontal stretch, horizontal this way, stretch or shrink, or vertical stretch or shrink. Now we're going to incorporate new information C. And this C is going to mean that there is a phase shift, which is going to be, as it says here, a horizontal translation or horizontal movement of the graph either to the left or right. So from pre-calculus, we know that this information inside the parentheses with the X like this represents a horizontal shift, and these are counterintuitive because if we see a negative C here, we're going to move to the right, and if we see positive C here, we're going to move to the left. Generally, we think if we have positive, we're going to go to the right, but this is kind of the opposite or counterintuitive to what we might think. So if bx minus c is what we have, then we are going to move, to the right. And if what we're looking at is bx with a plus c, a positive number there, then we are going to move to the left. So how we're going to use this c is we're going to make a fraction with it. We're going to take the c and put it over b, and that is going to give us our phase shift information. So let's take a look at this. In here we have, let's identify A, and now we have B and C too. A is 3 here. Our B is 2, and right in front of that X, so B is equal to 2. And then C is equal to here, we have pi over 3. And this negative sign says that this is going to be a shift to the right. So we know that our amplitude is A, and let's take a look now at what our period is. So period for sine is 2 pi, and it is over B, which in this case is 2. So our period is pi. So we are going to complete one cycle in pi, so in half the time it would normally take. And now in order to create our 5 key values, we're going to take this pi and we are going to divide it by 4. So this pi over 4 is what we're going to use to graph. So it's not our period, as we know. We're going to use this as our increment to graph. So now let's take a look at this phase shift information. We said that it's C over B. So our C is pi over 3, and now we divide that by our B, which is 2. And I know for me it's in the morning. I don't know when you're looking at this, but this is looking kind of ugly, this complex fraction here. So let's unpack this. We have pi over 3 divided by 2, which means multiply by the reciprocal 1/2. So we have pi over 3 times 2, which is 6. So our phase shift here is going to be pi over 6. And now because this was negative, we're going to go to the right. So instead of starting at 0 now, we're going to start at pi over 6 positive because we're moving to the right. So let's start getting our key values here. In the past, we started at 0. We're not going to start at 0 here because we have a phase shift. So we're going to start at pi over 6 instead. And now we add our increment, and our increment is pi over 4. So we have to add, to get here, pi over 6 plus pi over 4. And this is where this example involves work. I don't think it's so much the trig as fractions, and I know how much you all just love dealing with fractions. But here's what I'm going to suggest. Because we have to be adding pi over 4 as our increments, and we're looking at a pi over 6, looking at these denominators 6 and 4, let's create them in fractions that have same equivalent values but with the same denominator to make our life easier in terms of adding these things. So 6 and 4, the common denominator is going to be 12. So what I'm going to suggest is let's call this pi over 6 2 pi over 12. Same thing, same meaning here, but it'll be easier to add. And then this pi over 4 here, using a denominator of 12, this is going to be 3 pi over 12. Again, same equivalent information, but it'll be much easier in our life to be adding when our denominators are the same. So going back here to our starting point of pi over 6, I'm going to rewrite it using this 2 pi over 12. So this is 2 pi over 12 that we're going to start at. So now for our next point, we have our 2 pi over 12, and we're going to add our increment here, but instead of using the pi over 4 version, we're going to add the 3 pi over 12 version, and this gives us our next key x value of 5 pi over 12. So now we have for the next 5 pi over 12, and we're going to add our 3 pi over 12 because we keep adding the same increment. And this gives us 8 pi over 12. And yes, we can reduce that, but I'm not going to do that now because I just want to keep that denominator of 12 so we can keep adding. 8 pi over 12 plus 3 pi over 12. Again, same increment. Now we're at 11 pi over 12. And then for our fifth value, we have 11 pi over 12. And here we're going to add our 3 pi over 12 to give us now our 14 pi over 12. So we have our 5 key x values. Now we're looking at the sign of this information here, and this is going to be the same sign values that we have always gotten. We're going to have 0, we're going to go up to 1, back to 0, down to -1, and then at 0. So these values are the same. Now, if you wanted to, you could do a substitution in here to calculate the angles and then evaluate the sign of those angles. It isn't necessary. What we will do here is we'll do 1 just to kind of prove to you what's going on here. So what I arbitrarily did here is let's choose this value here. You could pick any. I'm just picking this one. No magic here. So we have 11 pi over 12. So this is the x we're going to look at. So here we're looking at the sign of 2 times this x. So we have the sign of here. We have the sign of 2 times this 11 pi over 12. And then minus this pi over 3 here. So this is what we're looking at now. So we can see inside here that 2 times 11, looking in here, we're going to have the sign 2 times 11, we have 22 pi over 12 minus pi over 3. And now this is the sign of 22 pi over 12. And now our pi over 3 here, we need to write that as 4 pi over 12 because we need those denominators to be the same, and in order to do the subtraction. And then we finally end up 22 minus 4. We're looking at the sign of 18 pi over 12. which is the sine of, we can divide both by 6, so we have the sine of 3 pi over 2. And now the sine of 3 pi over 2, we know that is -1. So there's our -1. So as I said, there isn't the need to go back and substitute all these x's in here. Because of how we've chosen these values, these will be our 0, 90, 180, 270, and 360 degrees that we're evaluating at. Finally, now that we have that, we have to take care of the fact that our amplitude is 3. So as in the past, our zeros stay the same. 1 becomes 3, and -1 times 3, -1 times 3 is -3. Finally, we can graph here. So moving on to our graph, we have the point 2 pi over 12, 0, or pi over 6. So instead of starting here at 0 the way we have in the past, we're going to be starting here. Now at 5 pi over 12, we're at 3, so we're up here. At 8 pi over 12, we're at 0, so we're back down at 0. At 11 pi over 12, we're at -3, so we are here. And then 14 pi over 12, we're back at 0. So notice on my graph here, I did reduce those fractions that could be reduced. So our 8 pi over 12 can reduce to 2 pi over 3, and 14 pi over 12 can reduce to 7 pi over 6. Is it necessary to do that when you graph? No, but it is a nice clean feature because we do reduce fractions, but for purposes of our graph, it doesn't change the information on our graph. So when we connect the dots here, here is the sine curve that we have known. Hopefully you recognize it at this point. And here in the original example, we were asked to graph one period, and that is indeed what we've done. So I want to take a look at this. The period on this, we can see the period here. And now let's check it out because we said that the period was pi. So if we look at our period here, we can see that we end here at 7 pi over 6 and we start at pi over 6. So 7 minus 1 is 6. 6 pi over 6 is pi. So there is our period. So we have done it correctly. And as usual, what I have done is I have graphed this on Desmos so we can get an appreciation of what we've just created and how that compares with our regular sine function when the period is 2 pi and the amplitude is 1. So here's 0, and now here is 2 pi. And here is, this green is a regular sine function, period of 2 pi, amplitude of 1. So we have a max at 1 and a min at -1. So here's how we would normally see a sine function. And then here, this is what we've just graphed. So if we look here, we can see this phase shift. Where we normally would start at 0, we can see we've shifted over and we're starting at pi over 6. We can also see the difference in our amplitude. Instead of being at 1, we're at 3, and then for the min, we're at -3 over here. The other change up we can see is our period. Our period takes place in pi. So for this one that we've done, we can see we start here at pi over 6, and then we complete our period here, which is 7 pi over 6, just like what we did by hand. Mine wasn't as pretty as this. And between here and here, 7 pi over 6 and pi over 6, that is a period of pi. So that's our period of pi. So you can see in this function, we are going to have two complete cycles in 2 pi versus our regular y equals sine of x.